Hello and welcome to this video. This video is on AVL tree. The name AVL comes from its inventors, Adolph Wolski and Landis. There were two Soviet inventors, Georgy Adolph-Wolski and Evgeny Landis. They did this algorithm, they invented this algorithm in 1962, and it is the oldest self-balancing binary search tree by date. So in AVL tree, the height of the two child subtrees of any node differ at most by one. If at any time they differ by more than one, rebalancing is done to restore this property. Lookup, insertion, and deletion all take O log n time in both the average and worst cases. So the performance is similar to red-black tree. Insertion and deletions may require the tree to be rebalanced by one or more tree rotations. So for search intensive applications, AVL trees are faster than red-black trees because they are more strictly balanced. So you can read this fourth bibliography or fifth one if you're interested in knowing the weight balance or new balance stuff. I will show you how the rotations occur. So suppose a node n comes, another node n, another node O, then we perform a left rotation. This is left rotation. And then we have right rotation, as you can see. Then we will have right left rotation and followed by left right rotation. So this graphics shows you how different rotations are performed. So that the rotations are the key part and maintaining the difference of heights is the key part. You can read various jargons on this and on Wikipedia. It is quite detailed and I will not go through all this. So what I will do is I will let you see the code. Again, this code has come from the GitHub repository of the algorithms. So we have an AVL node structure. It has three parameters, one the integer key, left and right children, and height. There is a max in function which returns a greater than b. If a is greater than b, it returns a, otherwise b. Very simple. For insertion, you malloc. If it is null, then we are out of memory. Otherwise, we assign key, make left right null, height as 0, and return the node. Node height is returned here if node is null is -1. Otherwise, return the height. Height difference, if node is null, you return 0. Otherwise, you return the left node's height and the right node's height. That is the height difference of a particular node. For minimum node, you go all the way to left and you return the node. For printing, we have if the node is not null, we take the right child and level +1 we assign and we iterate like that. At that level, we print the node and then we go on to left side and we print the node. It is just beautification, nothing great about it. And it can cause, it is not very correct also. There are problems in this. We see right rotate. What suppose a node Z comes, then what we do in right rotate is we find out its left child, okay, and we find the right child of left child. So something like this. We have right node or rather node Z, and then we take its left child. So this would be your Y. And then we take the right child of Y. So this would be T3. So what we do is we make Z Y right. Okay. So this node is disconnected here and here comes Z. Okay. Now T3, where does it go? We have stored the T3. But Z left becomes, this would be something like this. Y right, yes. And this becomes Z left becomes T3. So here it becomes T3. Okay. So uh, sorry, I made mistake. This was Y, and yeah. So Z was root. We took the Z left, we denoted as Y, and T3 is Y right. So now we have Y right as Z, and Z left becomes uh, Z left becomes T3. So here we have T3. So this node is no longer there. Oops. So this is no longer there. So this is how your right rotation is performed. You can manually examine this yourself by drawing the graphics. And then we set the height of red node as earlier. We take the max of node height of left and right and add 1 to that. And for you know, Y's height, we take the node difference of left and right, max of left and right, and we add 1 to that. And like right rotate, we have left rotate. And for left right rotate, we first left rotate the Z left and then right rotate the Z. And for right left rotate, we right rotate the right child of Z and then we left rotate Z. So this is the basic algorithm of or the core of AVL trees. Now we look at insert. So if node is null, we create the node and return it. The first check is if the node is not null, that key is less than node's key or not. If key is less, we go to left subtree recursively and insert. If it is greater than node key, then we go to the right subtree recursively and return. Then we calculate the height of the node by getting the left and right and add in 1 to that. Now balance factor, we assign height difference of the node as the balance. Now if balance is greater than 1 and key is less than node left key, then right rotate, accordingly left rotate or left right or right left rotate. For deletion, we similarly recurse and delete the node. If these are not the cases, sorry, I made a mistake. We iteratively recurse, and if key is equal, then the deletion will happen. If there are no children, then we take a left node, or if left node is not there, we take a right node. So in this case, what will happen is both the children are null. Okay. So this will be false, and because of false, this will be right. So that would be null. So it has no children. So it will become null here when there are no children. Now in that case, we assign node to temp and node to null, and finally we free the temp. In case of a single child, if there will be a child, suppose for example node left is not null, then what will happen? This will return node left. Okay. So in that case, this will be true and left will be returned. We see that node. And if left node is null and the right node is not null, then in that case it will return node right, which will be assigned to node, and then we free this. Okay. In case of two children, we find the minimum node of the right subtree. This is the successor of the node, and we accordingly call delete on this. So rest of the things I will leave you to. Then the balancing is done here. Okay. And after balancing, it is the same thing. And to find a node, we find as if it's a BST. So essentially, for most part, it is a BST. The key is this balancing, that you have to balance. And whenever you are inserting or deleting, you have to balance these nodes. And to balance, you need to find the height and the balance factor. Okay. So once you understand this, it is very straightforward code. And there are 3 iterations here. print, pre-order, in order, and post order. So I'll suggest that you run this. Although this print AVL is chaotic, it does not print very nicely. So maybe you can improve this. So I'll suggest you to run this code. I have run it once and it works nicely except for this print. So I upload this code in the Git repository, and or you can download it from the algorithms repository. And yeah, so I think that's all. I think that compared to red black tree, it is far simpler to understand this, but the balancing and left right rotation can be quite expensive in case of AVL tree. So insertion may be more expensive depending on the structure of tree, and deletion can also be expensive compared to red black tree, because in this case, if balance is greater than one, there is one right rotation, and in either case, either this case or that case, one right rotation, and after the rotation it may become less than -1. I don't know. Most probably it won't become left rotation, but I'll let you try the insertion of various nodes and use pen and paper to figure out what happens. So with this, I will end this video, and I hope that you find this video useful and informative. Thanks a lot for watching. Happy programming.